In this video, we're going to discuss phase changes and the equilibrium between the phases. So then we have something like water and it's at the freezing point. So water at 0 degrees Celsius, or water at the boiling point, 100 degrees Celsius. Let's think about what's actually occurring. So if I've got a solid, I have a nice arranged block of ice. All the water molecules have a reasonably ordered structure. Well, it's floating in a container. And around that container is water. Just free-flowing water. These water molecules aren't as nicely arranged. They're moving around, they're not held in place. These water molecules can bounce and work through each other and move to other places. For any given bulk material, we have my favorite graph in all of chemistry, which is energy and percent. At a given temperature, you'll have a distribution. There's some percentage at low energy. There's a greater percentage at a medium energy. There's some greatest percentage at some middle energy. But then as you get to higher and higher energies, your percentage goes down. There's less and less that have those really high energies. The idea is that at any given moment, a particle can have an energy anywhere along this distribution. So some of these water molecules are moving very quickly. They're bouncing very fast and hitting things with lots of force. But a few are moving really slowly, slow enough that they might kind of just wedge in and get stuck onto the solid water. They don't really have enough energy to keep freely moving. Now they got to find something to stick to. If all the ones around it do have the energy to keep bouncing around, then they won't adhere. But the slower energy ones can bounce into the ice and get caught. Well, the ice molecules also follow this graph. Some of them have very high energy, some have very low. If one in the middle has some very high energy, it's trapped as it bounces into things. And so it doesn't go anywhere, but it can transfer that energy to one on the outside. And it's possible that if enough energy gets transferred in, one of these breaks free and now has enough energy to roll around in the liquid. What we have is an exchange. There's a rate solidifying, but there's also an opposed rate melting. Exactly at the melting temperature, these two rates are equal. If you could successfully completely isolate the system thermally, allow no energy in or out, then whatever amount of ice you had, whatever amount of liquid water you had, those two would remain the same. The molecules themselves would exchange back and forth, but the amount of ice versus the amount of liquid would not alter. As you add more energy, you break up some of the solid, you get it flowing free out into the liquid, and eventually you can have enough energy that all your material is liquid but still at 0 degrees as you've broken the binding for the solid. That energy we have to add to overcome that, that's the delta H of fusion. The average distribution tends to be tied to the temperature. It's proportional to it. And so while we get them free so that they can move faster, the energy went into breaking the bonds to get them free rolling. So at 0 degrees Celsius, we have this exchange between the solid and the liquid. Well, this is also true at 100 degrees Celsius. If I had a container and it had some liquid water in it, and I had some gaseous water, well, they are all bouncing around. But every once in a while, one of those gaseous water particles can just get stuck back in the liquid. And every once in a while, several of the liquid bounce into each other hard enough to push one of them completely free out into the gas phase. There's an exchange rate again. There's a rate of vaporization opposed by a rate of condensation. At 100 degrees Celsius, if you have no extra energy being added or leaving, then these amounts will remain constant. If you were colder, then the average energy in the gas phase doesn't favor it continuing to stay the same, and it would begin to decrease to a point. If it was over 100, then your liquid would successfully be able to start escaping. More of its molecules could escape into the gas phase. There are some complicating factors with the pressure of that gas, which we'll address in another video. But this idea of an exchange back and forth as we go through a phase change, or if we are stuck at the temperature so that the amount of each material is constant. This is the process by which these phase changes occur. There's an exchange rate between one and another, as not every molecule has exactly the same energy. As our temperature changes and our energy distribution changes, we'll get more and more that are higher in energy if we're hotter, or more and more that are lower energy if we're colder. And as more and more of your material changes to one or the other, you're going to favor one of those states. So this is why as we heat up a material or cool it down, we favor swapping over to one phase versus the other.